Hello friends, I am Chandan. This is my handwritten notes. You can download it from the description. Now in last lecture, we just completed the steady flow energy equation. Now there is some steady flow devices like turbine, compressor, pump, nozzle, diffuser, boiler, condenser, and turbines. Let's apply this steady flow energy equation first on turbine. Okay, the first focus on turbine. So turbine means there is some assumption is there. There is a steady flow. Steady flow means no accumulation of mass or energy inside the control volume, and this is perfectly insulated. Perfectly insulated means there is no heat transfer through the boundary of turbine. So that means Q equal to 0. Q equal to 0. From here, this is Q equal to 0, and the change in kinetic energy and potential energy are neglected. So this is the assumption. These are the assumption of turbine. Okay. So first focus on that. There is steady flow. Steady flow. In that here, the first assumption is steady flow. So here a steady flow, that means you have to write the steady flow energy equation. This is the steady flow energy equation. Okay, so hi plus ci square by 2 hi plus h1. So here in last lecture hi means inlet, and here inlet is 1 and exit is 2. So here hi h1 plus c1 square by 2 plus gz1 plus q, that is equal to h2 plus c2 square by 2 plus gz2 plus w of turbine, because we only focus on turbine, so that is the work done by the turbine. Okay, now uh, now here next assumption is that this is perfectly insulated. That is perfectly insulated. That means here the q is equal to 0. So this q is equal to 0, and just write this formula, the same formula hi plus ci square by 2 plus gz1, that is equal to h2 plus c2 square by 2 plus gz2 plus w turbine. And next assumption is that there is a kinetic energy, change in potential energy and kinetic energy are neglected. So that is why the here in that equation the kinetic energy and potential energy neglected means this is the here this is the kinetic energy in both side. So this is neglected and potential energy are also cancel out. So from here you can get this data hi h1, and that is equal to h2 plus w of turbine. So from here you can calculate the w turbine, that is equal to h1 minus h2. And you see that when in turbine, in case of turbine, the h1 is always greater than h2. h1 is the specific enthalpy, at inlet, and h2 is the specific enthalpy at the outlet. Okay, so inlet enthalpy always greater than the exit enthalpy. So that is why the turbine work, that is the positive work. So here work done by the system, so this is the positive work. So that is why we can say that work done by the system. Okay, work done by the system. So this is the symbol of turbine. This is the symbol of turbine here. This is the symbol of turbine, and this is inlet, and this is the exit, and this is turbine for, and this is the work done by the turbine. So the formula of turbine work, that is equal to h1 minus h2, or if it is an ideal gas, you can apply this equation w turbine, that is equal to cp into t1 minus t2. Okay, so this is only applicable if it is an ideal gas. Okay, so now focus on the compressor. So just apply the steady flow energy equation on the compressor. So assumption, if there is a compressor, there is some assumption is there, that is steady flow. First assumption, perfectly insulated, and change in kinetic energy and potential energy are neglected. That means same as turbine. Let's try to understand what is steady flow. Steady flow means just steady flow energy equation, h1 plus c1 square by 2 plus gz1 plus q, that is equal to h2 plus c2 square by 2 plus gz2 plus w of compressor. wc, that means w of compressor. Now perfectly insulated means the q value is 0. So that is why the equation will be like this, that is h1 plus c1 square by 2 plus gz1 plus gz1, that is equal to h2 plus ct square by 2 plus gz2 plus w of control volume. And now there is a change in kinetic energy and potential energy are neglected. So that is why this is neglected here, kinetic energy, potential energy neglected, and here kinetic energy and potential energy are neglected. So that From here you can get this data Hi1 that is equal to H2 plus W of control volume. So from here W of control volume, sorry W of compressor, that is equal to H1 minus H2. And if you focus on the compressor, the specific enthalpy at the inlet is less than the specific enthalpy at the outlet. So that is why this negative, this is, you will get this value negative. That means negative value indicates that work done on the system, the work done on the system. That is why we, in compressor, we supply to run a compressor, we supply work to run a compressor. So the compressor, the work done formula for compressor, that is equal to H1 minus H2, and this is the negative value because work done on the system. And this is the symbol of compressor. Here this is the symbol of compressor, this is inlet, here this is inlet, and this is the exit, and work done into the compressor. Okay, now focus on the nozzle. Nozzle is also steady flow, steady flow devices. uh, so in nozzle there is some assumption is also there, that is steady flow, that is perfectly insulated. Perfectly insulated means no heat transfer through the boundary, and there is no work transfer, that means W is equal to 0, and the initial height, that is Z1, that is equal to Z2. From reference to inlet the height is Z1, and from the reference to exit the height is Z2. So basically in nozzle the Z1 is equal to Z2. Now steady flow energy equation means just apply this equation, steady flow energy equation, and perfectly insulated means Q is equal to 0. From here you can get this equation, So here W, that is work done by the nozzle, but here there is no work, so here there is no work transfer, so that is why Wn is tends to 0. So from here you can get this equation, H1 plus C1 square by 2 plus C01, that is equal to H2 plus C2 square by 2 plus Z2. Now in nozzle, nozzle Z1, that is equal to Z2. From here you can get, that is H1 plus C1 square by 2, that is equal to H2 plus C2 square by 2. Okay, so here consider it is a nozzle. Consider it is a nozzle, and nozzle have one is the inlet, and two is the exit, and here the wall are insulated. That means in this wall there is no heat transfer through this wall. Okay, so as the inlet area is large and exit area is less, so that is why the exit velocity is larger than entry velocity. Exit velocity is larger than entry velocity. So you can write that C2 is greater than C1. So from here, in this equation, apply this equation here. From here you can get this C2 square by 2 plus H2, that is equal to H1. From here you can get what is the value of C2. C2 equal to under root of 2 into H1 minus H2, under root of 2 into H1 minus H2. Okay, and if it is an ideal gas, then C2 will be 2 into Cp into T1 minus T2. Cp is the specific heat at constant pressure. And if it is a reversible adiabatic process, then you apply this equation, that is P2 by P1, that is equal to T2 by T1 to the power gamma upon gamma minus 1. From here you can get T2, that is equal to 2 Cp, that is equal to under root of 2 into Cp into T1 into 1 minus P2 by P1 whole to the power gamma minus 1 by gamma. So you can get this formula if it is a reversible adiabatic process. Okay, now focus on the diffuser. If it is a diffuser, that means there is some assumption is also there, that is steady flow, perfectly insulated, no work transfer, and Z1, that is equal to Z2. From here you can get this formula. So this equation, that is H1 plus C1 square by 2 plus, that is equal to H2 plus C2 square by 2. Okay, so this is the here this is the diffuser and this is the initial inlet area and this is the exit area. Inlet area is lesser than exit area, so that is why C1 is greater than C2. Okay, uh, and this is there is no heat transfer through this diffuser, so Q is equal to 0. And if C1 is greater than C2, from here you can get this equation, that is H1 plus C1 square by 2, that is equal to H2. From here you can get this, that this exit so inlet velocity. You can find the exit velocity of the inlet velocity of the diffuser. So that is equal to under root of 2 into H2 minus H1. Now focus on the boiler or evaporator. Just apply the steady flow energy equation of the boiler. There is assumption that is steady flow and change in kinetic energy and potential energy are neglected, and in boiler or evaporator there is no work transfer. So same way you can just write the steady flow energy equation, that is change in kinetic energy and potential energy are neglected and there is no work transfer. That is why the equation will be like this: H1 plus Q that is equal to H2. From here if you want to calculate the Q value, the amount of heat, that is equal to H2 minus H1. But as the H2 is greater than H1, so this is why there is a positive value and that is heat supplied to the system. That means H2 minus H1 is positive value, that means heat supplied to the system. Okay, now now if you focus on the condenser, just apply steady flow energy equation, that is assumption that is steady flow, change in kinetic energy and potential energy are neglected and no work transfer. Remember this assumption, that is very important. Now if from here you can get that is Q, that is equal to H2 minus H1, and here in condenser the H1 is greater than H2, so that is why this value is negative value, that is heat rejected by the system. So from here if you see the condenser, the heat is rejected from this system, heat is rejected to this system. Okay, now throttling process. If you focus on the throttling process, the example of throttling process, that is flow in a capillary tube, flow through a porous plug, mm, uh, throttling process, and partially opened valve or tap, flow through small opening, flow through orifice. These are the example of throttling process. So what is the assumption, that is characteristics of throttling, that is assumption. What is the assumption? That is steady flow, that is no heat transfer through the boundary, no work transfer through the boundary, and change in kinetic energy and potential energy neglected, always occurs high pressure to low pressure. If you apply this equation, if you first write on steady flow energy equation, and there is no heat transfer, that is equal to Q is equal to 0, there is no work transfer, W is equal to 0, kinetic energy are neglected and potential energy are neglected. So from here you can get H1, that is equal to H2. That means initial enthalpy, inlet enthalpy, specific enthalpy, that is equal to exit specific enthalpy. So as the enthalpy is equal to same, you can say that hence it is an isenthalpic process. Enthalpy is same, that means it is an isenthalpic process. If the entropy is same, it is isentropic process. But if the enthalpy is same, then it is known as isenthalpic process. Remember this data, isenthalpic process. So here H1, that is equal to H2, from here T1, that is equal to T2, and here if it is an ideal gas, then T1, that is equal to T2, and from here you can get E1, you can say that E1, that is equal to U2 if it is an ideal gas, and from here you can say that as T1 is equal to T2, you can say that P1 V1, that is equal to P2 V2. Okay, the only thing is it must be an ideal gas. Okay, so this is all about the steady flow energy equation. In every year gate paper, there must be one question in steady flow energy equation, from steady flow energy equation. So steady flow energy equation is very important. Uh, you can do practice, that is very important. Just this is the formula, and just you have to practice the question. So just focus on one question, and there is a 4 or 5 question is there in my notes. You can follow these notes, this topic is very very important for gate point of view. Okay, and your semester you can get question from study flow energy equation. Now focus on this math. Okay, try to read this math. Consider steady flow of air, Cp of air, that is equal to 1.005 kilojoule per kg Kelvin in an adiabatic passage. In an adiabatic passage. Adiabatic means there is no heat transfer. Passage. That means it is a type of nozzle. Okay, nozzle or diffuser. Okay, air enters the passage at 100 kilopascal. Initial pressure is also given and temperature, that is 500 Kelvin, at a velocity of 150 meter per second, and exit the passage at 510 Kelvin. Assume air to be an ideal gas and neglect gravitational effect. The passage is a dash. The passage is a dash. Basically, uh, basically you have to find out the value, that is exit velocity, and you can conclude that it is a nozzle or diffuser. Okay, it is a nozzle and diffuser. So first try to understand this. Here this is steady flow. So here in this question, this is here, there is a steady flow. That means here steady flow energy equation is applicable. And air, that is why Cp value is also given. So given here Cp, that is equal to 1.005 kilojoule per kg Kelvin. And here the initial pressure is also given. The initial pressure, that is 100 kilopascal. The initial pressure, that is 100 kilopascal, and initial temperature, that is 500 Kelvin. So here initial temperature is 500 Kelvin, and velocity, initial velocity, that is to 150 meter per second. Now here one thing also given, that is passage temperature, that is equal to 510 Kelvin. So just you have to calculate the value of the value V2, and you conclude that it is a nozzle or diffuser. If the value is a V2 is less than V1, then you can say that it is a diffuser. Okay, and if the V2 is greater than V1, then it is, you can say that it is a nozzle. So let's try to find out the value of V2, that is exit velocity. Now there is steady flow energy equation. That means you have to apply this equation, that is steady flow energy equation, that is equal to h1 plus c1 square by 2 plus gz1 plus q, that is equal to h2 plus c2 square by 2 plus gz2 plus w. So here this is a passage, so that is why z1 must be equal to z2. So that is why gz1 and gz2 cancel out, and there is no adiabatic process is given, so there is no heat transfer, and this is a passage, so this is why work is equal to 0. From here you can get this equation, that is h1 plus c1 square by 2, that is equal to h2 plus c2 square by 2. So here you can see that it is applicable for air. So just apply the ideal gas equation. So you can get this Cp value, that is h1, that is equal to Cp T1 plus C1 square by 2, that is equal to Cp T2 plus C2 square by 2. Okay, now here the Cp value, the in question the Cp value, that is 1.005 kilojoule per kg Kelvin. So this is in kilojoule. So that is why just put the value Cp, that is equal to 1.005, and initial temperature is 500 Kelvin, plus C1 initial velocity, that is 150 square by 2 into 1000. Why it is 1000? You have to convert this in kilo, so that is why there is a divided of 1000. So just remember this unit, that is very very important. If it is kilo, you must be divided into kilo. All the portion will be in kilo. So here the unit of CPT1, that is kilo kilojoule per kg. So that is why here it is also kilo. So that is why here 1000 is divided. 1000 is divided to convert it into kilo. Okay. Okay, understand this? Okay, now CP CPT2, that is equals to 1 CP value 1.005 into T2. What is the value of T2? That is 510 plus C1 square by 2. You have to find out the value of C2. Sorry, C2. That means you can find out this V2 value. Okay, V2 square by 2. You can say that V2 square by 2000 because in kilo. So from here you can get this data, that is C2, that is equal to 49 meter per second. That means the exit velocity is lesser than the entry velocity. That means it must be a diffuser. Okay. So so this is the answer. This is the answer of this question, that is 49 meter per second. Okay. So there is another question, steady flow energy equation question. So important question is there. You can read and try to find out the answer. All the notes link are given in the description. If you have any problem, any inquiry, you can message me. There is a Telegram group. You can join to this Telegram group to get update on that group. And there is another question. This is very important question. This is previous year gate question, and there is answer is also there. Okay, this is my handwritten notes, and here this is a question and there is the answer is also there. And you can get one question, 2 marks question from study plan energy question in gate paper. Okay, so here there is another question and this is answer is also given. Okay, now next chapter, that is unsteady flow. So in the unsteady flow, basically not asked in asked is in gate, but it is asked in UPSC exam. So just same, but you mm, uh, this is my handwritten notes are given on the description. You can just read the things what is written here. Okay, that is not important for gate point of view. Okay, and this is the unsteady flow, unsteady question also there, question and there is answer is also there. Okay, so here there is same question and there is answer is also there. Okay, there is another question and another answer is also there. Okay, uh, another question and another answer is also there. Okay, so this is not important for gate point of view. That is why I skip that unsteady part. Okay, you can find these notes and try to understand what is written in the notes. Okay, and there is a question and there is an answer. And in this chapter we just understand that what is the in first law of thermodynamics, we just understand that what is the first law of thermodynamics and what is the consequences of first law. That means heat is a path function, energy is a property, energy of an isolated system remain constant, and perpetual motion machine of one, that is first kind, that is basically impossible. We get the the definition of enthalpy, and we understand the heat transfer for different process. That different process means it may be constant volume process, it may be constant pressure process, isothermal process, adiabatic process, polytropic process. Okay, so in previous lecture all the things are covered. You can see that uh, that videos. Okay, now in polytropic specific, what is polytropic specific heat? What is Mayer's equation? That is Cp minus Cv, that is equal to R. We just completed that. And what is free expansion or Joule expansion or unrestrained expansion? Okay, that is very important. And what is the difference between free expansion and isothermal process? And what is the flow work? And just we have completed the steady flow energy equation, and the steady flow energy equation for turbine, compressor, nozzle, diffuser, boiler or evaporator, and condenser at throttling process. Okay, and just we have see that the unsteady flow process you can read from my notes. So this is all about the first law of thermodynamics. If you have any problem, you can comment me, and this is my handwritten notes. You can download it from the description. All the mechanical engineering handwritten notes are there. And like, share, subscribe my YouTube channel. You can, if you have any problem regarding any issue, anything you want to know, then you can email me or you can message directly, no problem. And like, share, subscribe my YouTube channel. Thank you. Okay.